Anybody else here in dynamics?
Unfortunately not. Or not me, at least.
Me neither, Isaac.
Yeah, I'm not either.
Edgar, weren't you in statics last semester?
Yes, I was.
Not doing dynamics this semester, though.
No, I mean I don't need it
Fair
because
enough.
I'm electrical, and
That's
when
fair.
I took statics,
Just for fun.
it's just for fun, pretty much. But yeah, no, I'm not in dynamics, man.
So you
Freaked
build
me
a
out. I
bunch
was like,
of
do I need
soft
statics?
circuit boards.
Yeah, I just I just add statics to my schedule because there was like not other engineering class available.
Yeah.
And I didn't have that much like of a background from engineering classes, so I just took that one.
Yeah.
But yeah, it sounds misleading because it's like, yeah, what do you take, like, because why not?
Yeah. It's a good bonus.
Yeah, I mean, I don't regret it. I mean, I learned a lot of cool stuff in there.
Joanne was saying, or somebody who took statics previously was saying that Joanne dragged us a lot further than they got the last time that class was taught.
Damn.
Yeah.
I feel we missed a couple of things, like the last topics.
Apparently they stopped at trusses or trusses.
Okay, homies.
Hey, Carlos.
Assuming you guys are doing all right. So we got a full lecture ahead, so we would need to motor on through here. So what I want to go back is I want to review briefly about sources. Okay. So here we go. So we were talking about independent power supplies. And remember, language is sloppy here. And the reason why it's sloppy is that they'll talk about, you know, a voltage source and a current source, but it's more detailed than that. Everything's a power supply because everything puts out voltage and current. That's the definition of power. So if I talk about, you know, I have a voltage source, what I really mean that it's a power supply with a constant voltage value, but it's also a variable current source because depending on the load, you can get different current values. I can have active and passive power supplies, okay? If I have a current source, they behave very, very, very similar. If it's active, remember the current has to come in through the negative terminal. If it's passive, the current has to be coming in through the positive terminal. So a current source is very similar to a voltage source, is that it's a power supply with a constant current value, but a variable voltage source. Now, if you were to read the textbook, which you would find very, very, very quickly, this stuff is really bizarre. Theoretical voltage sources, theoretical current sources, man, you're not gonna like the way they're defined. In fact, a perfect voltage source is actually a short. A perfect current source is actually an open. But I won't talk about that till a little bit later. But what I want to do here is to give you a sense of where I'm at with this thing here. I want to go through this example. And this example is a good example because it really, well, I don't know. You tell me. If they're a little bit out there when you start to look at what sources behave like and stuff like that. So this example is really to give you a sense of what does a current source behave like? What does a voltage source behave like? Okay, so here we go. What you find here in this example here is that we know that it says that the current and voltage source are connected in parallel with the resistor. Here's our 5 ohm resistor, and these guys are in parallel. Now suppose that this source is 3 amps. Calculate the current in the resistor and the power absorbed by the resistor. Now I'm doing a little bit of cheating here, but not too much. And the reason why I'm saying I'm doing a little bit of cheating here is that I know that this voltage source is in parallel with this 5 ohm resistor. I mean, what else could it be? So if this thing here is ground, and that's 0 volts, And this whole line up here, right? This whole line right up here, this line, because it's 15, that has to be 15 volts. So in other words, what the voltage source does, it fixes the voltage across the 5 ohm resistor, right? Because what else could it be? If this whole line here is 0, and we could see that there's only one resistor between the high and the low, this immediately tells us that the voltage across the 5 ohm resistor must be 15 volts. That's it. So if I go and I calculate the current, so if I look at A, so if I of the source is 3 amps, then what this tells me here is that the voltage across the 5 ohm resistor should be, I'm sorry, that's not what I was supposed to calculate. They asked the current. So the current of the 5 ohm resistors then should be the voltage across the 5 ohm divided by the 5 ohm. So in this case, it's going to be 15 divided by 5 gives me 3 amps. So in other words, the current of the 5 ohm resistor is 3 amps. And then it says go calculate the power. Well, if I now look at the power of the 5 ohm resistor, there's multiple ways that we could calculate it. We know the current, we know the voltage, so I could have calculated, I can calculate this guy like this, right? Because that's the true definition of power. Now we could use Ohm's law to rewrite this, but we know that this guy is going to be 15 volts, 3 amps. So this is, of course, 45 watts, which is positive because it's passive here. So now I got this here. What does this mean here? So what I want to do here is that I want to go back in this guy, and I want to look at the this circuit just a tiny bit more this time. And what I'm going to do here is that I'm going to make a copy of the circuit so that we could bring it in.
Hey, Carlos, a quick question.
Yeah.
So if that's the case, we're saying that there's no current running through the branch where the voltage source is in that case?
That's exactly what we're going to go through right now.
Cool.
So what we want to do here is that you probably remember there's a commercial for Fruit Loops and it says, right, follow your nose. Let's follow the current. Okay, so what we want to do here is that we want to follow the current. Or maybe the current in the circuit. And what we do know, we know that this little SOB is putting out 3 amps. And we just calculated that this guy is 3 amps. The only way this could be true is if the current through the voltage source tells us that the current going down this thing here is that. Definition. Any element that has voltage equal to 0, you call this a short. So the question is, what have we done? So if the source is 3 amps, this means here is that the 15 volt source is shorted out. And what that means here is that it neither supplies / absorbs energy.
Carlos?
In the circuit. Hold on a second real quick. It
Right.
neither supplies or absorbs any energy of the circuit. So its goal is to keep the 5 ohm resistor at 15 volts, nothing else. Josh,
Wait, so is it 0 volts or 0 current?
oh, it's 0 current.
Oh, okay, that makes a lot more sense.
You know what? I have to go back and correct my stupid mistake. For some reason, I'm thinking shorted. So if the current is 0, it's not called a short, it's called an open. Okay, so the 15 source is open circuited, as we say. It's been open circuited, and so therefore it has no current running through it. So its whole goal then is literally to just keep that 5 ohm at 3 amps. Thank you, Josh, for the help. So that's kind of out there when you think about it, right? You would think that just because I have a source that it has to be doing something in the circuit. Here, it does nothing. It has no power. So then the next question says, what happens if the source current is now changed to 5 amps? Well, the question is this. I mean, so did the voltage across the resistor change? No, because the voltage of the resistor didn't change. It still puts out that same amount of current. It's still going to get 3 amps of current. Since the 15-volt source has not changed, that means that the current of the 5 ohm is still 3 amps, and the power of the 5 ohm is still plus 45 watts. Nothing has changed. Why? Because what determines the behavior of that 5 ohm resistor is that voltage source, no matter what. So the question is, what actually happens then? Well, if we go and we look at this thing again, and we look at what's happening in the circuit, this time, what's happening? The circuit here has 5 amps, and we could see here that through this resistor, that didn't change. So that's 3 amps. This tells us that this time, the only way this could be true is that if I have 2 amps going down here. So in other words, with the 5 amp source, the current source is now making that 15 volt passive. So the behavior of the 15 volt source is now a passive voltage source.
Carlos,
Yeah.
was there something in the original problem that told us how many amps were going through the resistor?
Yeah, the voltage, the 15 volt source. Right? That guaranteed that I had 3 amps. Right? If I have 15 volts across that, according to Ohm's law, I could only have 3 amps going down. So that's what the original circuit told us. And since I didn't change that 15 volts in the second circuit, it's still 3 amps.
Gotcha.
I do have a question too, Carlos. What is that an up to number basically, as far as up to 3 amps? Like say the current was only at 2.
Then the 15 volt source, right? If I come and put in just, right? And I think that's Tim, right?
Yeah,
So from Tim, is that if I change this to what? You said 1 amp?
sure, 1 amp.
Then this tells me here that this guy is still 3 amps. So if I look at this in terms of KCL, the only way this could be true here is that if I had 2 amps going up, this would then tell you that the 15-volt source now is active and it's supplying energy to the circuit. So not only is the current source active, but the 15-volt source is active.
Okay, cool.
Okay, so moving on here, I'm really hesitant to even show you this, because it's, even if I tell you, you may not even believe me. But I will say this here, that shorts and opens are extremely important in circuits. Okay, I cannot tell you how important this is. And it's going to take you a while to get used to this. Okay, it's going to take you a while. So here we go. So what they call a short circuit this is what they typically call a short. And if you listen to people, you'll see that people mix up short circuit with open circuit quite a bit in everyday language. Yeah, my wife says, and I go, no, that can't be a short. If the light's not coming on, it's not a short. It's anyways. But what does a short mean? Typically, what you find here is that anytime you have an element where the voltage across this thing is 0, then we say this element is a short. So that means I could come in here and take this element and literally replace it with a wire. So you can replace with a wire. So where do you see short circuits at? So as an example, ammeters are shorts. So typically it's the ammeter that really costs the big part of the digital multimeter when you buy them. And the reason why is that you want a short, you want an ammeter to have as small possible of resistance. And so what you're finding here, I just got a question here in the 5A example. Are you talking, I'm not sure what the 5A example is.
Isn't in oh, never mind. I was seeing the second one you drew. I take it back.
Okay, so an example of an ammeter are shorts. That means if you have a perfect ammeter, that means we typically draw an ammeter like this. This ammeter can be replaced with the short. Okay, so when you're looking at a resistor, so if I have 2 resistors and we want to open up the circuit to measure the current between these resistors here, what you're doing here is that you're inserting here an ammeter. And when you do that, it's physically equivalent to doing this. like that. That's what a nanometer does. On the other hand, if you have an open circuit, which is typically called an open instead of an open circuit, what you're finding here is that you have literally set this guy up in such a way that the current is 0. So if supposedly we have a current that's behaving like this, then we say that this element is open. So in this scenario here, we can literally replace this element with an open circuit here. So you can replace this like this. And a very good example of this guy here is a voltmeter. Voltmeters, in theory, are opens. Now, why isn't a voltmeter an open? The reason why that is that the internal resistance of a meter is huge. So typically you get them to be of the order of, a couple 100 million ohms. And so that means then when you're looking at a voltmeter, you can replace the voltmeter with an open. So the way you measure voltages is that you put your voltmeter in parallel with the resistor here. So when you're looking at the path, as the current is coming in here, if you truly have an open, then as the current comes in here, all of the current goes in that direction. But that's not exactly correct. You have to have a little bit of current running through the voltmeter in order to measure what that voltage is. But that's why you don't have, they're not exactly opens. Only in theory are they open. But that's what you want to think about here. So the two important things is that ammeters behave as opens, voltmeters behave as opens. Ammeters are shorts, voltmeters are opens. I think I said it just the reverse here. Now, one of the things here that I'm not going to do here is that ideal voltage sources are literally wires, because it keeps the voltage of 0 always the same. Ideal current sources are always opens, because they always keep the current at 0 amps no matter what is going on with the circuit. But that's just kind of crazy, because that's not the way we really want to look at these things here. So here we go. I want to go to the last piece of the lecture, and I want to talk about dependent sources.
Carlos, could you go up just like 1 or 2 lines, please?
Yes, I will.
Awesome, thank you.
So we want to talk about dependent sources. There are sources that literally are controlled by voltages and currents. Okay? So dependent sources are sources that depend on a voltage or current elsewhere in the circuit. And what you find here is that probably the workhorse of the industry is what's known as the micro amplifier 741, and this is known as an operational amplifier. And if you look at your circuits kit, you have 3 of them in there. They're also called op amps. And this operational amplifier is a voltage, controlled voltage source. And what you find here is that it means this voltage control, this guy, this is really this. So it takes some voltage, and then what it does next here is that the source here then so it takes some, let me go back here. It takes some controlled voltage, and what it does here is it amplifies it at the voltage source. So if you were to really look at this thing, so in an op amp, they call this guy here the input voltage, and they call this guy here the output voltage. So when you look at what the value of the source is, you find that it's V output is equal to some constant. This is what they call the gain times V input. So if V input is 1 and A is 1, you get a 1 volt output. But if I change the input voltage to, let's say, like 10, then my output voltage in this case would be 10 volts, or it could be 100 volts, depending on this thing here. And so what you're going to find here is that you're going to find that real dependent sources consist of 2 parts or 2 pieces, right? One has to be the controlling voltage, and the other one has to be the voltage source here. So the first piece here is what is called the controlling element. Okay. And this is the independent piece. And so in the beginning, what we're going to do here is that this is the voltage / current of a resistor. And then later on, we'll bring in more complicated things. And then the second piece here is that this is the controlled element. So this is the dependent piece. And this dependence piece is in the voltage or current source. So what I'm going to do here is that to make things a little bit cleaner, whenever I have a controlling element, this implies that it's either the voltage across a resistor, which I'll call VC, or the current through a resistor, which I'll call IC. And then the controlled element will then say here that if I have a voltage source I'll call this VD, whereas if I have a current source, I'll call this ID. So let's look at these things. So what you find here is that there's going to be 4 kinds of sources here, right? So there are 4 types of dependent sources. So let's list them here. So the first one I'm going to do is what's known as a voltage controlled voltage source. And so you could see my acronym, right? Voltage VCVS. So I'll call this VCVS. So the way we do this here is that we look at a resistor here. So here's my resistor. All I know is that this resistor is somewhere in the circuit. And because of this resistor, I know for a fact that I'm going to be pulling off the voltage across this resistor. And what you find here is that the way we draw a voltage controlled any dependent source is that we draw diamonds. So diamond immediately tells you that it's a dependent source. So then check this out. I know that this is my voltage VD. So what do I find? I find that this guy, according to what we wrote up here, right? According to what we drew up here, the output and the input, you're going to see that this VD is then going to have some type of proportionality constant. And in this case here, you're going to see that this is the controlling voltage. So the value of this dependent voltage source has some scaling factor A1 and VC. So if I look at the units of A1, it must be volt per volt. So A1 is a scalar. So the voltage across the resistor, which is the controlling element, is what controls this voltage source here. So then we can have another one. The other one that we could have, instead of a voltage controlled, it could be a current controlled. Voltage source. And so this acronym, of course, is then going to be CCVS. So when I go and I look at my resistor this time, I'm not interested in the voltage. I'm interested this time in the current. So when I go and I draw this guy here, it's still a voltage source and it still has a value of VD. But now you could see that this thing is going to be directly proportional to the current. It's the current through that resistor that does that. So I should have a different scaling constant or gain. And in this case, if I look at the units of A2, you could see that they got to be volts per amp. And then I can go through the other 3 here. So now I'm going to have what? I could have the opposite, which is a voltage controlled current source. And of course, this is VCCS. Again, I look at my resistor and I look at my dependent source. And so in this case here, I'm pulling what? For this resistor, I'm pulling out the controlling voltage across this resistor. And what you're finding here is that now I have a current source. So if I have a current source, I can put that current source any way, any direction that I really want to, because we're not talking about passive or active, but now I have a dependent source. And so I'm going to have a different gain. And you could see here that this is my controlling variable. So if I look at my units of A3 in this case, you can see that it's got to be amps per volt. And then the last one is a current controlled current source, which is CCCS. So we can now sort of like get a sense of what is going on with these guys. So now this guy's pulling off the current element. And so when I look at this gain here, you could see that this gain has units of amps per amps. And that's what I mean by a dependent. So those are the 4 types here. So one example, just to, these are from my office hours earlier. Let me delete these. Okay, hopefully I don't have any more of those guys popping up. So just to give you an example here, some simple examples. It looks something like this. Suppose that I have an element a circuit that looks like this here. And what you're seeing here is that I have some resistor here, I have some voltage source here. And what I'm saying here is that this guy is a dependent current source, and it's going to depend on some gain A, where the this is a current controlled current source, where this guy is this current IC. Now, if I look at this IC here, I'm going to say that this guy is 8 amps. I mean, how did I come up with those values? They're arbitrary. So my question is if I know that the current in this branch is 32 amps, what is the gain of the current controlled current source? So in this case, what is A? Well, for starters here, I can see here that ID is equal to AIC. And I could see here that this current ID must be 32 amps. So I know for a fact, just by looking at this, in that branch, I have 32 amps that are flowing. But because this dependent source depends on the current IC is over here by this 8 ohm resistor. And we could see that in this case, this has to be 8 amps. So you could see that I'm getting the current from somewhere else on the circuit. So this tells me here that the gain in this circuit, A, has to be then 32 over 8 amps per amps, which is, of course, a gain of 4. In other words, I am taking this guy from a different location here. Now, let's look at this slightly different here now. As another example, let's think about this circuit here. And what I'm going to do here is that now I'm going to insert a voltmeter right here. And over here, I'm going to insert an ammeter here. Okay, so what we find here is that I have a dependent voltage source, and this dependent voltage source depends, let's call this is a voltage controlled voltage source, where I'm going to call this 1, and this guy is V1 right there. You know what? I called this a nanometer. My bad. That would kill that resistor. And you know what? I don't like that purple 32, so I'm going to bring this down so I could separate it. So here's what we know. I know that the red lead is right here. I know that the black lead is right here on the voltmeter. And I know that this guy here is the black lead. And this guy here is the red lead. So when I take my voltmeter and I measure this guy reads 2 volts. The blue here reads 8 volts. So when I look at this thing here, the question is, again, what is the gain? Well, for starters here, you could see that I'm taking my voltmeter and I'm measuring the voltage across the source. So you could see that the voltage across the dependent source must be A V1. But that value must be 8 volts because just as the previous example, there's only 2 nodes across that voltage source. When I go and I measure the voltage across the V1 resistor, we could see here is that V1, according to the voltmeter, it tells us that it's 2 volts. So then this tells us here that we have that 8 must be A times 2, which then tells us that the gain in this case will be 4 volts per volt, 4 volts per volt. And so again, I'm taking the voltage somewhere else in the circuit to actually measure this thing. So to wrap this up, what I'm going to do here is that I'm going to go in, and I'm going to get this last example that I'm going to do. And here it is. And so what I'm going to do here is that I want to determine this constant G. What's G? It's the gain of what kind of a source is this? You could see that the dependent source here, right? The dependent source, this guy's going to be, what kind of a source is it? It's a current controlled voltage source. And then G is the gain. So what we want to do here is that we want to use conservation of power to actually do this here. So we're going to use conservation of power to determine the gain G, assuming that the circuit is good. So the first thing that I need to do here is that I need to go figure out what is active and what is passive. Okay, so let's go do this here. So the first thing that you're seeing here is that if I look at the left branch, you could see that the current here is entering the negative terminal. This guy's entering that. So therefore, we know that this guy has to be active. This guy has to be passive. Okay. And what we're seeing here is that if I look at this current IX, note that the current IX is also in the flow of the 4A. So right away, I could see that this current here that's flowing in this branch here, which is IX, but note that IX and 4A are exactly the same. So you know what? These reds, I don't want to mix them up with the other one, so I'm going to change the color so that it's easier to see where I'm putting in. So what I'm seeing here, IX in this case, tells me that this element over here, because it's entering the positive, must be passive. So according to our sign convention right here, you could see that I have 2 amps coming in here. So in this branch, you could see that this GIX looks like it's active. So if this is the case, then let's go look at this thing here. So according to conservation of power, we know that the active sources must equal all of the passive, the active elements must equal all of the passive elements. So in this case, we've identified that the 14 volt is active, and we could see here that the GIX source is active. And then for the passive elements, we see that the power of the 2 volt plus the power of B. Maybe I should have been calling them A and B. I have a tendency to do. I probably should have said A and B to make him a little bit easier. So let's go look at this thing here. So if I look at the 14 volt one, you could see that I have 2 amps coming in. So this is going to be 2 times 14. Now, what's the power of the element GX? Well, it's got to be, remember, power has to be voltage times current. So in this case, what's the voltage? It's called GIX times the current. And in this case, the current is 2. Then the 2 volt is then going to be 2, but note that 2 amps goes all the way around. So that's 2 amps coming in here. So that's going to be 2 times 2. And when I get to the 12 volt, you're seeing that I'm going to get 12 volts. And then I have IX, but IX is 4. So then I could come in and actually start to go mathematically solve this equation. So let's go. So you're seeing here that this is going to give me 28. Now look, I'm going to put the 4 into here. So I get 4 times 2, which is 8. So I'm going to get 8G. And on this side, I'm going to get 4. And then I'm going to get 12 times 4, which would be 48. And if you do the algebra, we see here that G then must have a gain of what? 3. But what are the units of the gain? Well, in this case, we know that the voltage divided by the amps are the proper units. And I'll stop right here. And that's how I use conservation of power to get the gain for that dependent source. Now, what I'm going to do here is that there's one more example that I was going to do. And I'm going to skip that example. It's in my lecture notes. And I'm a little pressed on time because we really got to keep moving, in this, where we're at here. So what you're going to see here is I'm going to move to the next chapter right now. Okay. So everything that is on the homework and the quiz, there's one small problem like the last example that I was looking at, but we need to press into the next chapter. And the next chapter is on resistive circuits. So I'm going to change my sheets here. And I'm going to go towards this guy right here. I'm now in the next chapter. And in this chapter here, let me make this a little bit smaller. In this chapter here, God damn it. Is chapter 2. We're going to be dealing with resistive circuits. And I want to tell you that, in my opinion, this may be the most important chapter in this course. This is about whether you learn to see series and parallel. And I'm purposely going to make this as challenging as possible, because I'll tell you this much, if by mid-semester, especially, let me change what I said. by the time we get to the differential equations in chapters 6, 7, and 8, if you have not mastered this chapter, I recommend that you drop the class. It's that simple. Because what we're going to do here is that we're going to lead to some very, very, very powerful theorems. In other words, I'm going to be able to rewrite Kirchhoff's laws so that you get some really powerful theorems and super, super, super easy to use. But when we get to nonlinear circuits, you have no choice but to use the techniques of this chapter. And it's so crucial that you gotta master this here. If you're gonna spend a lot of time on one chapter, this is the chapter that you want to spend on. So here we go. What we're gonna be talking about is the basis of all low voltage circuits, Kirchhoff's laws. Without any doubt, Kirchhoff's laws are the governing laws of electric circuits. Without any doubt whatsoever. And remember what I mean here is that we're talking low voltage circuits. If you have low voltage circuits, you can't use Kirchhoff's law. Everything that we're going to derive in this chapter, so all of the techniques that we derive here in this chapter are from Kirchhoff's laws. And I know that in Physics 4B, you guys probably used Kirchhoff's laws, to try to analyze maybe a 2-loop circuit or something like this. Those techniques that you used in 4B are horrendous, like really horrible. And what you're going to find here is that the techniques that we're going to develop are way more powerful. In this chapter, we're going to use something called the voltage divider rule or the current divider rule. And man, do they make stuff a lot easier. And then in the next chapter 3, we're going to get into these very, very powerful techniques where we really rewrite Kirchhoff's laws into a way that's usable. And those are called mesh and node theorems. Now, all of these techniques here, so the techniques in this chapter I call simple circuits, okay? And what it really does when you use simple circuits, you essentially identify what is in series and parallel, right? Exactly what you learned in Physics 4B. Not really. You're going to see that this is on steroids. So, and remember, this is challenging. I expect you to be very challenged by what we're going to be doing here. So what we want to do here is that we want to start talking about what do I mean by Kirchhoff's current law, Kirchhoff's voltage law, what are nodes, what are loops, etc. So we need some very basic definitions. So here's our first definition. Okay. Our first definition is a node. A node is a fancy word for equipotential. So a node is an equipotential surface. A node is a junction of,
Carlos, could you move up one line, por favor?
like right here,
Perfect, thank you.
is a junction of two or more elements. Okay, so that's, in no time you'll be an expert at counting these guys because we're going to keep practicing on them. So what we want to do here is that we want to go in and give you a sense of what. So my question that I'm going to ask now with this circuit here, how many nodes are there? So let's look at this. So I have, let's say that I have this circuit that has this many elements. And so I'm going to draw these guys like this. Question, how many nodes, how many junctions are there in this circuit here? Well, if we count them, one of the things that you're going to see here is that here's where it becomes super important to probably have pins that have multiple colors. Because I'm looking for junctions with two or more elements. Well, note that here's one right here, right? That's two elements. That's one junction between two elements. And another thing here is that if you look here, know that all of this is one junction. And so by using colors, what you're doing here is that you're being able to identify which junction are you talking about or which node are you talking about. And if I look at my other node here, you could see that this guy could be another one. And what you're seeing here is that one way that you can draw this to simplify this thing is to take all the wires. They are wires. I mean, you probably wouldn't want to wire it this way in a circuits lab, but another way that you can draw this thing here is that you can draw it like this. Right? You're reducing everything here. So you could see here, here's my red, here's my green, and then here's my violet. So in this case, you could see that I reduced it. So in this case, I have how many nodes? I have 3 nodes. And then I can do another example. If I look at this example, and how many nodes do I have in this case? Well, the way I do it is I just start coloring wires. Remember, they're equipotentials, so they must have the same. So if I look at this guy here, there's one right there. I could pick another one right here. And then I have this guy. And then lastly, this guy right here. So if I look at how I'm coloring these guys, in this case, I have 4 nodes. So your ability to identify nodes becomes super, super important here. So what I want to do here is that I want to go in and I want to start to bring in Kirchhoff's laws. And what does Kirchhoff's current law have to say about all of this stuff right here? Let's go look at that. So Kirchhoff's So we don't say Kirchhoff's current law, it's more common to say KCL. Okay. So KCL says that the algebraic sum of all of the currents entering in any node is 0. Right? So it says the algebraic sum of currents entering any node is 0. Now it turns out that I don't know, I don't really like that sign convention. A lot of textbooks do use it, but what does it look like mathematically? And I'll show you what I mean. So it says here that for all of the currents coming into some node, that the sum of these guys is 0. So that means you need a sign convention. And what this really means, it's really the sum of them going into node minus the sum of the currents going out of node. So typically, the way I write this thing is that I don't write it in this form. I just look at this thing as, like I said before, the signs are going to be horrendous. Or you could ignore the signs and just say all of the currents coming into the node must equal all of the currents going out of the node. And when I say KCL, this is what I mean by KCL right here. And so what I want to do here is that I want to look at an example here, just to give you what the sign convention is. So imagine that this is the node that I'm looking at. So this is my example. Okay. So imagine that I have a current coming in. And let's say that I have this current going out. And maybe I have this current going out. Oops, I can't count here. And then maybe this current coming out too. So in this case here, what you're seeing here, according to my law here, or the way I write it, I go like this. I look at this thing and I just say, how many are coming in? Clearly, I1. How many are going out? Well, 1, 3, 4. This is KCL right here. Now, if you follow the sign convention that many people use, so if you use this guy now, and if this makes more sense to you, then this is what you do here, and they do this here. So a current coming into the node gets a plus sign here. If I have a current going out of the node, then this current gives you minus I. So that's the sign convention. So if I look at that same example over here, right? So if I take this example here, and I bring it over here, then I could do the same type of thinking here. Well, here I go. So then I start to sum all of the currents. So the sum of all of the currents here, look at 1. 1 is positive. But if you look at 2, 3, and 4, it's got to be minus 2, minus 3, minus 4 equals to 0. But then if I do the algebra, you see I get the same thing. But note that that's an algebra step. Note that you got to deal with the minus signs. This is why this is my preferred way of doing this thing. Okay, this is why this is my preferred way of doing these things. So as a further example, let's go look at an example that I have in my lecture notes, and it looks something like this here. So what I have here is I have a node, Here's another example. And what you're seeing here is that I have wires that look like this. And what you're finding here is that you're given 3 nodes. This is X, Y, Z. And now what you're seeing here is that there's currents that are coming in. So this is a current 5 amps. This is a current -1 amp. This is a current 7 amps. And all you know here is that there's a current here, which I'm going to call IA. I'm going to call this current in this branch B, but I don't know what the direction of this thing. And then there's a current here, which I'll call IC, and this current here, I'm going to call ID. So the question is this. What are IA, IB, IC, ID? Okay, so let's look at this thing here. So the first thing that I'll do is I'll start off at the simplest place, node X. Why node X? Because note that the currents here are, there's only 2 currents coming into X here. And so what you're seeing here at node X, the current coming in is IC, the current going out is ID. So therefore, these guys must be what? Equal. Okay, now let's go to node Y. So if I look at node Y, I got to pick a direction for IB here. Well, it seems like a reasonable direction for the current might be in this direction right there. So I'm going to say that IB is going in that direction. So let's go look at KCL. So I look at how many currents are coming into Y. So when I look at this thing, I see that the currents coming into Y is going to be IB plus ID. What's the current coming out? IC, right? The currents in equals the currents out. So in this case here, IB then says that this is IC minus ID, but note that that's 0 right away. So I don't know what the current IC or ID are, but I can say that IB, without any doubt, is 0. So IC and ID are arbitrary and don't really matter. It just means here that the current in that branch must be the same. So now let's go look at node Z here. So here we already know that IB is 0. So now what I'm going to do here is that I'm going to look at the same thing. All of the currents in must equal all of the currents out. So here I go. So what's in here? Well, in is IA. What else is in? I got flop 5. But look at that -1. It looks like it's coming in, but if I switch sign, it's actually going back out. So then I have IA plus 5 is coming in, but then I really have 7 plus 1. So you could see here that IA in this case has to be 8 minus 5, so it must be 3 amps. And that's my preferred way of applying KCL to get currents at the nodes or coming in or out of nodes. Okay, I'm going to move on to the next thing. I just defined a node. Now I want to define a loop. So when I go and I do this, what we're going to find here is that I have I need a new definition in order to apply Kirkhoff's laws. So a loop is a closed path formed within a circuit. Okay, so this is a very simple definition. And I just want to remind you that what this really means here is this, that when I have a loop, what I'm really saying is that if I look at the work done by an electric force in some loop, because this is a conservative force, it's always zero. And because it's always zero, I could take any closed loop, and I know that the work will always be zero in this case here. But what you find here is that what's proportional to the work is potentials. So this tells us about that potentials must sum to zero around a closed loop. That's what that's really telling us. So, question. How many loops are possible? So if I look at this guy, what I'm going to do here is that I'll draw a fairly straightforward loop here. So how many loops are possible in this case here? Well, we can draw them, right? So for starters here, the easiest way to think about it is just say, well, there's one possible loop. Here's another possible loop. And then here's another possible loop, right? So that those, you know, at the surface, it looks something like this. Now, what you're finding though, is that typically when you draw exactly what you see, that's actually the number of independent loops, which are what I actually drew right there. And it's really about like the theory of equations. I'm sure you never got taught that, but you can also do the following thing. I could pick this loop, and it turns out that this loop is now dependent on other loops, or I could pick this loop instead, or I could come all the way around this thing like this so that you get 6 loops. But only 3 are independent. And later on, I'll show you what that means in the next chapter, what this means here. So what this tells us here is that anytime I take Kirkhoff's voltage law, I'm going to have to do this type of thing. I have to pay attention to the loops here. So here we go. This is Kirkhoff's voltage law, which we lovingly call KVL. And KVL says that the sum of voltages I should be more careful. Maybe voltage drops around any closed loop is 0. In other words, what we really say here is that the sum of all of these voltages is 0. And what you find here is that what this really means is this, that if I go around a loop and I see something with if the current goes this way, then we call that a positive. Let me be very careful here. I'm not being very nice here in my language here. So if this is positive and this is negative, and the current is entering the positive node, okay, the current is entering the positive node, then we call this plus V. If I have an element where now the voltage across this guy has opposite polarity, but the current is still coming in this direction, then Kirchhoff's law says I got to write this as a minus. And so this guy here is our second Kirchhoff's law. Okay, our second Kirchhoff's law. And so what we should do here is to get to sort of like a experience with this thing here. What I want to do is that I want to come in and look at an example of this guy. And this is my example here. So it says here that determine the power absorbed by each of the resistors in the circuit. Now note that I am using Kirchhoff's laws right now. If you use Kirchhoff's laws in the quiz that you're going to be taking on Wednesday, read my lips. I will give you 0 for that problem. If you want me to put in Kirchhoff's laws into the first quiz, I can do that. But I'll tell you, the quiz is going to be much more challenging. I want to only focus on the material from the chapter 1, not chapter 2. So just consider yourself warned. So the first thing that I'm going to do here is that I'm going to go in and I'm going to count the number of nodes, right? Because that's what we really want to do here. Okay? Question. How many nodes? Well, for starters here, I'm going to come in here and I'm going to say wherever I have a wire, so I got 1, right? Here's 2, 3, 4, 5, and then finally, I'm going to say this is 6. So I know that I have 6 nodes. Now, since we already did 3 loops already, we know that this will also have 6 loops. So we know the number of loops, but remember, there's really 3 independent loops here. So the only thing that we could say here is that I'm going to focus on elements where I know for a fact what about what values that we could have here. Well, for starters here, in circuits, it's customary to start putting in grounds right away. But since we haven't really done that, I'm not going to do that. So I'm going to focus on Kirchhoff's voltage law here. So here we go. So the first thing that I'm going to do here is that I'm going to do what I would expect to do here is that I'm going to look for anything that I have either a current source is in series with an element or a voltage source is in parallel. So the first thing that you note here is that note. So I'm going to focus on resistor. How about the 8 ohm resistor? And what you're seeing here is that when I look at that 8 volt, note that this immediately tells me that the voltage across this guy must be 8 volts. Okay, it must be 8 volts. So then this tells me here is that the voltage across the 8 ohm resistor is 8 volts. So then this tells me here that the power of the 8 ohm resistor is going to be what? Well, I could do it like this, but I don't have the current. So we want to do it without the current. So I can rewrite this like this. So if I do this, this is then going to be 8 squared over 8. So therefore, I'm going to get positive 8 watts for the power across the 8 ohm resistor. So now what I have here is that I have the power of that resistor. So then what's the next easiest thing to do? Well, the first thing that we can do here is that I know that this is 8 volts, but look at this 6 volt one. If I'm going to be going to the left here, what I'm going to do here is that I'm going to focus on the 6 ohm resistor. Now, what's special about this 6 ohm resistor here, let me go get this image because I think this is worth getting here. Right? If I get this guy here, look what happens. If I use Kirkhoff's law, okay, I'm going to use KVL to get the voltage across the 6 ohm. Now the question is, I have to define the polarity of the 6 volt source, the 6 ohm resistor. I don't know what the polarity is, so I'm going to guess. So I'm going to come in here and I'm going to say, this is plus, this is minus, this is the voltage across the 6 ohm. So now what I'm going to do here is that I can make any closed loop to calculate what the voltage across that guy is. So let's do that. So now KVL tells me here, so look what I'm going to do now. I'm going to pick any direction that I want because it's path independent. I'm going to go in this direction right here. So my path is going to be like that. So here I go. If I go up, you're going to see that I'm coming to the 8. Note that I hit the negative for the 8 volts. So then I'm going to write this as what? Negative 8 volts. I come all the way down. I come all the way around. Up at the top, I get plus 8 volts. And then I come and I hit the positive for the 6 ohms. And then I'm coming all the way around. And then I hit the negative sign. And this is 12 volts. And that must be equal to 0. So that means here that the voltage across the 6 ohm, you could see that these guys are going to do what? They're going to cancel each other out. So then this guy tells me that this is going to be 12 volts. And you know what? I'm out of time. So I got to stop. I will put this, I'll post these up sometime later on today when I get it. But otherwise, I will see you guys later, okay? Remember, quiz on Wednesday. You lab people, I'll see you tomorrow in lab on Tuesday. All right.
Have a good
Later
one,
on,
Carlos.
guys.
Thank you, Carlos.
Thanks,
Hey,
Carlos.
thanks for showing up, man. I appreciate it. Okay, bye.
Absolutely.